Here's one of our wind-up toy cars, a force measuring device, and a weight on top of the car. The weight is there so that when we pull back on this device, the wheels will not slide but rather turn in contact with the surface here, and thereby store up energy. So if we pulled the cart before the weight on top fell off, we were exerting a force between 2 and 2.5 newtons on the Newton balance. If we turn the car around, and this ramp is level, the angle of the camera is such that it doesn't look that way, but it is pretty much level. If we turn this around, we can pull the car with a force of only about 0.5 newton. So we see that there isn't a whole lot of friction resisting the motion except for the friction in the wheels when we turn the car backwards. We see that 0.5 newton force is sufficient to keep the car moving forward, but it takes 2.5 to go this way. This implies that, for example, if we roll the car back 10 centimeters, we should store up an energy in the wheels that's equivalent to a force of 2.5 newtons acting over a distance in this direction of 10 centimeters. And then when we release the car, we should regain that energy in the form of kinetic energy. Or perhaps we might change the incline and allow the car to move up the incline, measuring how far the car actually travels as a result of the force. So we see that by storing up kinetic or potential energy in the spring type mechanism that runs the car, okay, we store up energy, and we can measure the amount of energy we store up by pulling the car one way, then pulling it the other, and seeing what the difference in the force is, assuming that the work done by the difference of the force goes into the wheels or into the spring mechanism that drives the wheels. We can then determine how much kinetic energy the car is capable of gaining, and we can determine how high the car is capable of climbing, how much vertical elevation the car can gain as a result of that energy.